So in this video, I want to go over an alternate method for optimizing a function on the boundary of some disk or some curve. Okay, so this specifically is only going to work when we are optimizing on the boundary. Okay, so not within the boundary like the previous problems we've done. So in those problems, we were considering the critical points, right? But here, we're only going to be looking at the boundary points. And this is helpful because the boundary points are often, very the hardest part of those problems, or at least the longest part of those problems, right? In all of the problems we've done so far, the critical points just took a couple of minutes right at the beginning, and then the bulk of the time is spent on the boundary. So that's why this is important. Now, I know for a fact that this isn't actually used in the statistical theory classes or probability theory classes. So this is more of like a bonus method, not necessarily something you would see in those classes, but I still wanted to include it because I do think it makes certain problems a bit easier. Okay. So this does involve one thing which we have not covered, which is known as the gradient. So this is in more like vector calculus that we skipped over a lot of the vector calculus stuff that you would normally see in like a Calc 3 class just because it's not really relevant to statistics. The gradient actually is kind of relevant to statistics, specifically a generalization of the gradient called the Jacobian. Okay, so I'll just write that down. It's very relevant in multivariate statistics when you're working with matrices and stuff like that. But that's not really what this class is meant to prepare for. This is more just for the, statistical theory class. Is not for multivariate statistics. So that's why we're not really going over it in this class. But anyway, so I'll go over the gradient really quick. What the definition of it is very simple. So let z equal f of xy such that fx and fy exist. Okay. Then the vector, which we write like this. So this is written as, or read as the gradient of f, is called just that, the gradient of f. The gradient of f and is defined as gradient of f of xy is equal to the partial derivative with respect to x times I hat. So we'll just write it like this. Okay. Again, we sometimes put hats over the vectors. I don't really like to do that because that means something different in statistics, right? So fy of xy times j. Okay. So this is a vector then, right? So remember that this is the vector 1, 0, right? And this one right here is the vector 0, 1. So you could write this in component form just as well. Okay. So this really has a lot to do with like this plays into the concept of like directional derivatives, which is not something that we went over. That's another thing we cut from this class. So that's why we didn't really go over this. And I wasn't sure if I was going to include Lagrangian multipliers or not, but I think it's worth mentioning as, again, an alternative method. So this is not something that you'll have to do in optimization problems, but it's another thing you can do for the boundary points specifically. So let's get into the method then. Okay, so this is, we'll just call this Lagrange multipliers. So first we'll state the theorem behind the method, and then we'll go through the actual method itself in steps. So this says let f and g be functions of two variables, but it can be extended past that, with continuous partial derivatives at every point of some open set containing the smooth curve g of xy equals 0. Okay, so g here is going to represent the constraint. So notice that there's an equality in there. The fact that it's equal to 0 is no issue because you can just move everything to one side and then it's equal to 0. But it's an equality, not an inequality. So that's what I meant by this will only work on the boundary of some curve, right? The idea of a smooth curve, we don't really need to worry about. Smooth just means kind of just what it sounds like, that it's smooth, meaning it's differentiable. There's no sharp corners. It's continuous, all that kind of stuff, right? So suppose that f, when restricted to the points on the curve g of xy equals 0, has a local extremum at x0, y0, and that the gradient of g at that point is not 0. Okay. Then, in that case, there is a number, which we usually use lambda for this number, called a Lagrange multiplier, for which the gradient of fx0, y0 is equal to lambda, and then the gradient g of x0, y0. Okay, so lambda here is just going to be a scalar. Okay. All right, so now we want to get into, okay, that's nice that there's this number here. This number is relating the gradient of f to the gradient of the constraint g. But how do we put this together and then solve for what that point x0, y0 is, right? That's what we're interested in. We're interested in finding that local extremum. So how do we find it now? So I'll write out the method here. Okay, so the method, one, would be set up a system of equations where we have the gradient of fx0, y0 equals lambda times the gradient of gx0, y0. So that equation that we just had up here. And then we also know that this is true, right? This is the given constraint. Using this, we want to solve for x0 and y0. Okay, so we'll look at an example, of course, and we'll see that this system of equations should let us solve for those points. And then the largest of the values of f at the solutions found in step 2. Okay, so there might be more than one point right here, is what it's getting at. So whichever one of those is the largest maximizes f. Okay, so in other words, this is going to give us all of the candidates for the points that could be the maximum. And similarly, it'll give us the points that will be candidates for the minimum. So I won't write that down because it would say the same thing, right? All right, so let's do an example now and see how this actually works in practice. So let's say we're given the function f of xy equals x squared plus 4y squared minus 2x plus 8y, subject to x plus 2y equals 7. Okay, so same idea of the previous optimizations problems that we were doing. Just, those were over closed sets, and this one is over just this is just going to be a plane, right? So it's just on this the before, like if we were looking at x plus 2y is less than or equal to 7, we would still be considering the points where it's equal to 7, and we would call that the boundary. So that's what I mean by we're only working on the boundary. But this is how the problems would typically be set up, but you could still use it to look at the boundary specifically for those points. Okay. All right, so first thing, we want to transform this to be equal to 0. Okay, so this is our g function, g of xy. Okay, so we bring everything to one side, doesn't matter what side. And then we want to set up that first equation, okay, which is the gradient of f is equal to lambda times the gradient of g. Okay. So let's go ahead and find this then. So the gradient of f would be the partial derivative with respect to x. So that's going to be 2x minus 2 times I hat plus the partial derivative with respect to y, that's 8y plus 8 times j hat. And that's equal to lambda times, same thing with g. Okay, so maybe I'll write it like this. So partial with respect to x is actually just 1. So that's just going to be I hat. And then with respect to y is going to be 2. J hat. Okay. So expanding this part out, we have lambda I hat plus 2 lambda j hat. Okay. So we can set the different components equal to each other then. Right, so we know that 2x minus 2 must equal lambda, and 8y plus 8 must equal 2 lambda. Okay, and now this is not enough for us to actually solve the problem. Now we need to go ahead and use this restriction as well up here. Right, this x plus 2y minus 7 equals 0. Okay, so let's throw that constraint in here. X plus 2y minus 7 equals 0. Okay, so now we have a system of 3 equations with 3 variables, including lambda. So it can be a little bit trickier to solve here. We can immediately eliminate the lambda variable because we have that lambda is equal to this, so we can go ahead and say, okay, this is 2 times 2x minus 2, because that's what lambda is, right, which is 4x minus 4. So we can just work with these bottom two equations. 8y plus 8 equals 4x minus 4, and then x plus all this equals that. This one, we could just go ahead and solve that for x. So this is going to be 7 minus 2y. There might be an easier way to do this via elimination, but this way looks set up for this way well enough. So we have 4 times 7 minus 2y minus 4. Okay, from that second equation then. So now we can just solve for y. So we have 28 minus 8y minus 4. So that's 24 on this side minus 8 is 16 on this side, 16y on this side. And this makes this y equals 1. And I really should have had the zeros on here to emphasize this is actually a specific point that we're solving for. I usually just tend to omit them and just remember that it's a specific point because I don't want to write them every time. But if we want to be proper about it, we should include all of these zeros here to, again, emphasize that this is a specific point that we're finding. Okay, so that's what was the system of equations here, was the x zeros and y zeros. So we have that y zero is equal to 1. We can go ahead and plug that in right here to find x zero. So this tells us that x zero is equal to 5, not 6. And that is the only point that we're getting here. Okay, so the lambda is kind of like a dummy variable here. It's not, we don't actually come out with an answer for it. We can get an answer for lambda. Like you can plug in 5 for x0 in that first equation there, right? And you get that lambda is equal to 8. But it's not really important. It's more just a dummy variable to kind of get us to that xy point. Okay. So anyway, this tells us that we have 5, 1. This problem actually asks to find a minimum, so it's not expecting us to check that it's a minimum. I didn't write down that part, but we could check just via the second derivative test, for example, right? So the second derivative test, d, the second partial derivative with respect to x is going to be 2. With respect to y is going to be 8, and the mixed partial derivative is 0. So this is greater than 0. fxx is greater than 0, so this tells us it's a minimum. Okay, only a local minimum. Okay. But that's really our only candidate here, right? We don't have a, this doesn't have a boundary per se itself. So there's an infinite number of points on this line. So we may not have a global max or min there.